Have you ever found yourself just staring at a mountain of information? Articles, reports, research, and you're just wishing you could instantly get the core insights.
Yeah, those aha moments.
Oh, yeah.
Without drowning in all the details.
Exactly. Such common challenge. And, well, the world of AI, taking all that messy text and turning it into something a computer can actually understand, that's where embedding models come in.
They really do shine there.
Think of it like a giant pile of laundry that's your raw text. Embeddings are kind of like magically sorting it into neat stacks, comparable stacks.
Yeah, by color, maybe fabric type.
Right.
Something the computer can work with. Numbers, basically.
Right. Numbers computers use to make sense of it all for search, recommendations, that kind of thing.
And for a long time, the main way was using dense embeddings. These are usually pretty compact vectors, maybe a few hundred dimensions, and most values are non-zero. They're efficient, sure, but sometimes a bit of a black box. It's hard to tell why you got a certain result. But there's this really fascinating alternative that's been gaining a lot of traction lately, especially now with sentence transformers v5,
Okay.
sparse embedding models. They offer this unique blend of, well, efficiency, but also, crucially, interpretability.
And that's our mission today, isn't it? We're doing a deep dive into what these sparse embedding models actually are.
Yep. Why they're powerful, how you can train them.
And how they stack up against other methods. We're really going to unpack why you might want to explore these high-dimensional but highly interpretable vectors for your next big project. So let's start with the basics. When we say sparse here, what does that actually mean? Because, common dense embeddings are usually lower dimensional.
Right, like 384, 768, maybe at 124 dimensions.
Yeah.
And packed, like you said, most values are non-zero, dense.
Okay.
Sparse embeddings. They completely flip that. They produce high-dimensional vectors. We're talking 30,000 dimensions, maybe even more.
Wow. Okay. 30,000.
And this is the key thing. Most of those values are zero, hence sparse.
Okay. Makes sense.
And what's really interesting, truly intriguing, is that each non-zero value often corresponds directly to a specific word or token in the model's vocabulary.
So it's not just an abstract number. It links back to a word.
Exactly. And the direct link is where you get this amazing interpretability. It's like a window into how the model is, quote-unquote, thinking.
Okay, give me an example. How does that work in practice?
Well, the sources mention this Naver-SPLADE v3 model. If you feed it a sentence like, the weather is lovely today, it generates this huge 30,522 dimensional embedding. But the cool part, the really game-changing part, is you can actually decode it.
Decode the embedding.
Yeah, you can see the top 10 tokens, the words that contributed most strongly, along with their activation scores. So for the weather is lovely today, you might see weather and today pop right out with high values.
So it's not a black box at all. You can literally see which terms the model thinks are important for that sentence.
Precisely. You can interpret it. And that's not just for understanding one text in isolation.
Right. You mentioned comparing texts.
Yes, it gets even more powerful there. You can compute the intersection or the overlap between two sparse embeddings. This is super useful for figuring out why the model thinks two texts are similar or dissimilar.
How so?
So compare the weather is lovely today and say it's so sunny outside. The decoded intersection might highlight common conceptual tokens like maybe weather and cool, showing you the shared concept.
I see. It explicitly shows the common ground.
Exactly, which is something dense embeddings just can't really do in that same direct, interpretable way.
Okay, so we've got a handle on what they are, these high-dimensional interpretable vectors where most values are zero. But that leads to the big question, the so what? Why would you, listening now, want to actually use these?
Well, the primary reason, I'd say, and a key differentiator, is something called query and document expansion.
Expansion.
Think about traditional methods like BM25. They can only match the exact word, the exact tokens that are present in the text.
Yeah, word-for-word matching.
Neural sparse models. They automatically expand the original text with semantically related terms, terms that mean similar things.
So going back to the weather example.
Exactly. The weather is lovely today. A sparse model might expand its understanding to include terms like beautiful, cool, pretty, even nice.
Even though those words weren't in the original sentence.
Correct. Or, it's so sunny outside, might expand to include weather, summer, sun. It's bringing in related concepts automatically.
Wow, okay. That ability to go beyond exact matches, that sounds like a massive improvement for search.
It really is. It lets these models match synonyms, related ideas, even if the wording is totally different.
So it helps with that whole vocabulary mismatch problem, where people search for one thing, but the document uses a different word for it.
Precisely. It handles that. It can sometimes even help with misspellings. That's why these models often outperform traditional lexical search while still being efficient because of the sparsity.
Are there any, downsides to that expansion?
Well, there's a small caveat. Sometimes it can be too expansive. Like the example given is if you search for Tuesday, it might expand to related terms like Monday or Wednesday.
Ah, which you might not want.
Right, depending on your specific need. But for most general semantic search tasks, that expansion is a huge plus.
So it feels like sparse models sit in this interesting middle ground. They're not quite the old lexical methods, but they're also different from the dense embeddings we often hear about. What are their main advantages, the core selling points?
Yeah, they occupy a really valuable niche. I think it boils down to three main things for you to consider. First, hybrid potential. They mix really, really well with dense models.
Hybrid, so using both sparse and dense together.
Exactly. Especially for complex searches where you need both that precise word matching and the broader semantic understanding. You combine their strengths.
Okay, that makes sense. What else?
Second, interpretability. We keep coming back to this, but it's huge. You can see exactly which terms, which tokens are driving a match. That's gold for debugging, for understanding, for building trust in the system.
Absolutely. And the third?
And third, just raw performance. They can be very competitive, sometimes even better than dense models, on many information retrieval tasks, especially when that lexical precision matters.
Okay, interpretability, hybrid potential, strong performance. Very compelling. But you mentioned earlier that out-of-the-box models might not get domain-specific terms, right? Which brings us to fine-tuning.
Yes, fine-tuning. This is crucial. Because while a general pre-trained sparse model is good, it probably won't know your specific jargon, your industry's synonyms.
Like the medical example.
Exactly that example. The source mentioned the patient complained of severe cephalalgia. You or I know that means headache.
Right.
But an untrained model might just see cephalalgia and expand it into, well, meaningless subword tokens like hashtag tag KV or hashtag tag KV or hashtag tag Kyria, praying tag Gia, not helpful at all.
So it doesn't make the connection to headache.
Not unless it's been trained on data where that connection is clear. And this isn't just medicine, right? Think about tech, Java the language, versus Java the coffee, or finance or law.
Yeah.
Every field has its own language. Audi makes cars, not audio gear.
So fine-tuning is basically teaching the model your specific language, your domain's vocabulary and synonyms.
Precisely. It allows a model to learn and focus exclusively on the nuances and relationships within your data. It makes it much, much more effective for your specific needs. You're customizing its world knowledge.
Okay, so fine-tuning is key for specialized domains. Let's say you're convinced you want to do this. How do you actually train one of these models? What are the pieces involved? Let's start with the model itself. What architectures are there?
Right. The architecture is the blueprint. The sources highlight three main options you can choose from. First up, you've got SPLADE models.
SPLADE? Okay.
Think of these as your general purpose, highly interpretable choice. They usually start with a standard language model like BERT, Roberta, Distilbert, one of those masked language models. And they add a special pooling layer on top. It's called SPLADE pooling. It essentially forces the model to represent the text by activating specific vocabulary tokens. This is actually the default if you just give it a standard fill mask model.
And this is the one that gives you that really clear interpretability we talked about.
Yes, exactly. Because the output directly relates to vocabulary words.
Okay, what's the second option?
Second is Inference-Free SPLADE. The name kind of gives it away. Its main selling point is really fast query processing at inference time.
Faster queries, how does that work?
It cleverly shifts most of the computational work to the document indexing phase, something you can do offline ahead of time.
Ah, so the heavy lifting is done before the user even searches.
Right. It uses something called a router, which directs queries down a very lightweight path, while documents go through the full SPLADE process during indexing. For training, you just need to tell it which inputs are queries and which are documents, and maybe adjust learning rates differently.
Interesting trade-off. Faster queries, but more work upfront indexing.
Potentially, yes. And maybe a slight hit to performance compared to standard SPLADE. But the speed gain can be significant.
Got it. And the third type?
Third is contrastive sparse representation, or CSR models. These take a different route altogether. They essentially add a sparse autoencoder layer on top of an existing dense sentence transformer model.
So you start with a dense model and make it sparse.
Kind of, yeah. You're learning a sparse representation from the dense one. But a key difference here is that the dimensions in a CSR embedding don't directly map back to vocabulary words like in SPLADE.
Ah, so you lose that direct word-level interpretability.
You do, yes. They're sparser, but not interpretable in the same way. They tend to work best when you apply them to really high-dimensional dense models, maybe 124 dimensions, or even up to 4096.
Okay, that's a clear breakdown. SPLADE for interpretability, inference-free SPLADE for query speed, CSR for sparsifying existing dense models.
That's a pretty good summary.
So if you're listening, here's a quick architecture picker guide. Want to make an existing dense model sparse? Look at CSR. Need instantaneous query speed and okay with a possible small performance dip. Inference-free SPLADE. For everything else, especially if you want that clear interpretability, standard SPLADE is probably your best bet.
Sounds about right. But the architecture is just one piece. You need other things for training too, right?
Absolutely. What else is essential for fine-tuning?
Well, obviously you need a data set, your training data. This can come from places like the Hugging Face Hub. Look for data sets tagged, sentence transformers, or just your own local files, CSVs, JSON, whatever.
And the format matters, I assume?
Critically, the structure of your data, like the column names, anchor, positive, negative, or query document, label, score, and the order, must match what your chosen loss function expects. Got to feed it the right stuff.
Okay, data set format is key. What's next?
The loss function. This is basically the math equation that tells the model how well it's doing and guides it during training. It calculates the error and helps the model adjust.
And for sparse models, there are special ones.
Yes, you'll typically use things like SPLADE loss or CSR loss. These have mechanisms built in to encourage sparsity to push most of those embedding values towards zero. Or for advanced stuff like distillation, you might use sparse and messy loss.
Gotcha. Loss function guides the learning. Then what?
Then you have training arguments. These are mostly optional, but they let you control the training process. Things like where to save the model, output year, how many times to go through the data, num train pox, the learning rate, whether to use mixed precision FP16 for speed, all those knobs and dials.
It's a control panel, essentially.
Yeah, exactly. And crucially, you need an evaluator. You can't just rely on the training loss number going down.
Right. You need to know if it's actually getting better at the real task.
Precisely. The evaluator runs the model on a separate data set and calculates concrete metrics, like retrieval scores. There are specific ones like Sparse NanoB evaluator that work well with benchmarks, or Sparse Triplet evaluator. You want an evil data set that's big enough to be meaningful, but small enough that you can run it fairly often during training without slowing things down too much.
Find that balance. Makes sense. And the last piece?
The trainer. This brings everything together. The Sparse Encoder trainer class is the conductor of the orchestra. You give it the model, the arguments, the data sets, the loss function, the evaluator, and it handles the whole training loop for you.
Like taking Distilbert and fine-tuning it on, say, natural questions using this trainer?
Exactly that kind of scenario. It orchestrates the entire process.
Okay, so those are the core components, but I know there are usually more advanced tricks, ways to really boost the process or get more insight.
Oh, absolutely. And some of them are really quite slick in how they integrate. Take callbacks, for instance. Yeah, these are little functions that can run in different points during training. Things like the WAN-B callback, if you use weights and biases for experiment tracking, it automatically logs everything for you. Or TensorBoard callback, even one called Code Carbon callback.
Wait, Code Carbon, what's that?
It actually tracks the estimated carbon emissions of your training run.
Wow, okay, that's neat. And these just work.
Often, yes. If you have the underlying libraries installed, like WAN-B, TensorBoard, Code Carbon, the trainer often just picks them up and uses them automatically. You get all this extra logging and insight without much extra effort.
That's pretty convenient. What else?
Another really powerful technique is multi-dataset training. Sometimes you have relevant data spread across different datasets, maybe even with different formats or optimal loss functions.
And the trainer can handle that?
Yep. The Sparse Encoder trainer lets you feed it a collection of datasets. It can then sample from them intelligently during training.
How does it sample? Does it just mix them randomly?
You have options. Round Robin takes one batch from each dataset in turn until one runs out. The default, though, is proportional. It samples more often from the larger datasets, making sure it sees all the examples from all datasets over the course of training. Really flexible.
Okay, this is where it gets really interesting for me. We know what they are, why use them, how to train them, even advanced techniques. But the proof is in the pudding, right? How do these sparse models actually perform, and how do you best deploy them?
Right, the results. Looking at benchmarks like NanoSMR Marco, the performance story is quite compelling. So a sparse model on its own might get, say, 52.41 NDCG at 10.
Which is a standard search quality metric. Higher is better. Okay.
A dense model alone, maybe around 55.40 NDCG at 10. So dense slightly ahead there, perhaps.
Okay.
But here's where it gets exciting. Hybrid. Remember combining them.
Yeah, using both sparse and dense.
Using a method like reciprocal rank fusion to combine their results. The performance jumps significantly to 62.22 NDCG at 10.
Wow, that's a big leap. Much better than either one alone.
A huge leap. It clearly shows that leveraging both sparse lexical signals and dense semantic signals is really effective for improving search quality.
So the synergy is real. What about re-ranking?
Good question. Adding a re-ranker on top, whether it's after sparse, dense, or hybrid, consistently pushed the scores even higher, up to around 66.3 NDCG at 10 in the example.
So first, retrieve candidates, sparse, dense, or hybrid, then use a more powerful, maybe slower model to re-rank just the top ones.
Exactly. It shows that a good re-ranker can really polish those top results, but it also leads to an interesting practical insight.
Which is?
You could potentially replace a standard dense re-ranker pipeline with a sparse re-ranker pipeline. Why? Because sparse embeddings can be much cheaper.
Cheaper.
Fewer active dimensions means less storage space. Example mentioned maybe 180 active dimensions per document for sparse, compared to 1024 for a typical dense model. There's way less data.
And potentially faster retrieval, too.
Yes, especially with those inference-free sparse encoders we talked about. You could get near-instant first-stage retrieval, almost like BM25, but with better semantic matching, then apply the re-ranker. Could be faster and cheaper overall.
That's a really practical angle. Faster, cheaper, good results. Any key tips for actually achieving that strong performance during training?
Two main things stand out from the sources. First, when you evaluate, don't just look at the retrieval scores like NDCG, also monitor the actual sparsity of your embeddings.
Why sparsity?
Because if your embeddings aren't actually very sparse, if lots of values are still non-zero, you lose those storage and speed advantages. You want high scores and high sparsity. It's a balance.
Okay, track both score and sparsity. What's the second tip?
The second is about how you train. The strongest sparse models often aren't trained just on simple text pairs or triplets. They're trained using distillation.
Distillation, like learning from a teacher model.
Exactly. You use a more powerful, maybe slower model, often a cross-encoder, which directly scores how relevant a document is to a query as the teacher. The sparse model learns to mimic the teacher's scores.
So it gets more nuanced guidance than just, this is relevant, this isn't.
Right. It's more complex to set up. You need that teacher model and its outputs, but it often leads to the best performing sparse models. Definitely something to consider if you need top-tier results.
Okay, great tips. So you've trained your super sparse, high-performing model. How do you actually deploy it at scale?
That's where vector databases come in. You need a system designed to handle these high-dimensional sparse vectors efficiently.
Like Qdrant, OpenSearch.
Exactly. Options like Qdrant, OpenSearch, Elasticsearch, Seismic, many are adding or improving support. Qdrant, for example, is highlighted as having good native support for sparse vectors, handling the storage efficiently and enabling fast retrieval.
So you encode all your documents using your trained sparse model, index them in a vector DB like Qdrant.
And then when a query comes in, you encode the query, send the sparse vector to Qdrant, and it finds the most similar document vectors very quickly. That's how you put it into production.
We have certainly covered a lot of ground here, really taken a deep dive into this world of sparse embedding models.
It's a fascinating area.
Absolutely. From that unique interpretability, being able to actually see the activated tokens to their power in hybrid systems and the potential efficiency gains, they really offer a compelling alternative.
They definitely give you a different set of tools, different trade-offs to consider compared to just dense models.
Which brings us to a final thought for you, our listener. Given everything we've discussed, the interpretability, the speed, the performance, the hybrid possibilities,
how might using a sparse embedding approach change how you think about building your next information retrieval system, your next search engine or recommendation engine? What possibilities does it open up for you?
Something to definitely mull over. We really encourage you to explore these ideas more, maybe check out the Sentence Transformers library, look at models like SPLADE. Thank you so much for joining us on this deep dive today.